This is the source code for our Model Context Protocol server, or MCP server. At the top, if you haven't seen this before, this is some script metadata to allow the UV package manager to automatically install the dependencies we need and then run the Python program. It's sort of like pip requirements files, but integrated into it. So we can just do UV run the file, it'll fetch all of our dependencies and run it all together. So this is what an MCP server kind of looks like. You define your tool functions. You can do it with an async function. In my opinion, you should. It makes it so your server can run multiple requests at once. If you're doing what I'm doing here, where you're doing something locally, it definitely doesn't matter, but it's free, so why not? As I mentioned earlier, this server's sole purpose in life is to send a UDP packet and receive the response and get that back into the artificial intelligence model that called the tool. So that's what this function is doing. It's using the Python socket library to send raw data out over UDP, get the result back, and then return it as text context back to the model. It does return errors if things go wrong. Basically, the only thing I've seen go wrong is if the destination isn't actually listening to the protocol, it will not, it'll time out, so it'll get a timeout error, but everything else, it's just shuttling bytes back and forth. It doesn't care about protocol level specifics. This method lists the tools, as you can tell by the name of it. There's probably some way that I don't know to automatically populate this list instead of manually typing it out for every tool function you have, but like I said, I don't know it. The most relevant thing to know is that the descriptions here are passed into the model, so you want your descriptions to accurately describe in as much detail as you think is necessary to the model what the parameter types should be. And then required fields, if you have fields you don't care about. For me, the timeout is the only non-required field. If it's not specified, I think it defaults to like 5 seconds or something like that. This method is the function that will get called when the model tries to invoke any tool on the server. It gets the name of the tool. So we just do a simple if statement. If it matches, we run our tool. If it doesn't match, it means they're trying to call a tool we don't support, so error out. If you don't know what SSE is, it's a JSON RPC protocol. The way it works is a server, when it connects, gets a session ID, and then they send messages back and forth from the actual messages bus. And that's what this, I don't know what to call it other than hierarchy, represents. On connect, it creates a scope and a server session, and then when a when something posts to this last messages endpoint with a transaction ID, it'll be handled by the post message function, which ends up calling our tool call functions and all of that good stuff. This is what it looks like when it's running. Nothing too fancy, just a running server. If we go to that in a browser, it doesn't really tell us much, as you might expect. But if you go to like SSE, you can see that we got ourselves a messages session ID. And then if we go to that URL, you can see that we'll get an error because it can't parse our message because we didn't send one. To test our MCP server, we'll use Copilot's MCP integration, mainly because I have Copilot Pro but not Claude. There's a couple ways to use MCP servers. I'm going to use HTTP server sent events. After specifying the server URL, we can name our MCP server. I don't know if the name matters to making it easier for the model to discover it, but it can't hurt, so I'll pick an informative name. We can start the server in the settings view, then check the server output and see that Copilot found our tool. You can make the server available to the model by enabling it as a tool or by explicitly including a given tool as context. With that done, we can prompt our model to send a packet using our tool and see the output. Unsurprisingly, the request times out as there is no server on the other end of the packet. Putting the model to work, I wanted to see how well LLMs can function as a DNS client. I ran the test using GPT-4o and Claude 3.7 Sonnet as the models. As you can see, GPT-4o completes very quickly, successfully determining the right format for a DNS request, sending it, and giving us the results. Claude takes much longer, iterating many times on both figuring out what hex encoding is and on the proper format of the request. It's also considerably more verbose in how it gets there, which makes sense since Claude is designed to be more of a reasoning model. After a little reassurance, it does eventually get there, taking a little over 4.5 minutes to succeed at resolving Google.com via DNS. I hope you enjoyed learning about impractical artificial intelligence with us. Next time, we'll see if we can make an LLM be a natural language compiler.